Okay, so in this video we're going to look at Euler's method. And Euler's method is used to approximate a differential equation. As you've seen, there's some differential equations we don't have the skills to solve. You'll learn those when you take Diffie-Q in college. But so sometimes we just want to approximate a differential equation, and we can do that with the Euler's method. So this is actually what Euler's method is. It's an iterative process which gives a numerical method to approximate the particular solution. And I've sort of given you the formula here, and I know this makes very little sense to you, but I promise you as we do many of them, it's pretty simple. Basically, you're going to be given an initial condition just like you normally are, and we're going to call that initial condition x is 0. Then we have to determine the step size. The smaller the step size, the more accurate your answer will be. Either the step size will be given to you or you'll have to determine it, and it's pretty easy to do that. So you're going to be given x of 0, and then x1 would be x of 0 times whatever your step size is. What you're going to do is evaluate the differential equation for the previous x and the previous y values. That's why we start with x of 0. So we evaluate the differential with the previous x and the previous y. We multiply that times our step size, and then we add the previous y. And then we do that for the second one. And again, we continue that process until we get to the value that we want. Again, the smaller the step size, the more accurate your answer. So let's do an example. And of course, this is in your notes. So this is our differential equation, x plus y. Now, at this point in your math career, you cannot solve this differential equation. But you can estimate its value at x equals 1. Now, in this case, we're given the initial condition. Our initial condition is when x is 0, y is 0. And we're told that we want to do this with 2 steps. Now, it should read using 2 steps of the same size. So you can't take a step a quarter and then 0.75. You have to use 2 steps of the same size. So having said that, if I start at 0 and I want to get to 1 and I want step size, I want to use the same size step, then my step size, or delta x, should be, you got it, 0.5. That'll give me 2 steps of the same size. So you want to start by just writing your table. So these are my x values and my y values. So I was given the initial condition 0, 0. And since my step size is 0.5, that means that I'm incrementing my x value by 0.5 each time. So my next x value would be 0.5, and my last x value would be 1.0, which is where I'm trying to go. I'm trying to get to 1.0 using 2 equal step sizes. So I've set up my x values. Now, how do I find my y values? Well, remember, in the previous slide, let's just go back for a second. We said that y1 is equal to y sub 0, which is the initial condition, times delta x times the differential equation evaluated with the previous x and previous y. So my next y value, well, let me write it here. So I have y1 is equal to y of 0 plus delta x times my differential equation evaluated at my previous x and my previous y. Okay? So let's take it step by step. My previous y is 0. My delta x is 0.5. Now I am evaluating this differential equation, which is x plus y, using my previous x and my previous y values, which gives me 0 plus 0. And of course that's 0, and I get 0 again. Well, that looks like it didn't help, but it did. So now we're going to do it again. I take my previous y value. So this previous y value comes here. My delta x is 0.5. And I'm evaluating this x plus y using my previous x. Well, my previous x now is 0.5. My previous y is 0. And then I get that approximating this at 1 would give me approximately 0.25 or 1/4. Okay? Now some of these you will need to use a calculator. This could show up on the calculator active or calculator inactive section. Generally it shows up on the inactive because I think there's a program that you can put in your calculator that will do it for you. So they generally like to give it to you on inactive so you won't have your calculator to do it. Okay, second one. This time we kind of switched gears here and did t, but you know what? Let's just go ahead and change this back to x for now just so it won't confuse us. Now notice this differentiable only has x in it. It does not have any y. So my previous y when I'm evaluating will not make a difference. Also, yes, I could integrate this and find what y equals. But we're going to use Euler's method with 4 steps to approximate y of 1. All right, so if I start at x equals 0 and I'm trying to get to 1 with 4 equal steps, what size steps should I use? So I'm trying to go from 0 to 1 in 4 steps. You got it. So my step size should be 0.25. So I'm going to set up my table. I have x. My initial condition, I started with x is 0, and then I'm increasing by 0.25. And you could use fractions if you like. I don't know why I'm using decimals because I generally prefer fractions. And my initial condition was 0, 1. I said 1 and wrote 0, but let's fix that. Okay? All right. So remember, to get my next value, I take my previous y, I add that to my to the delta x times the function evaluated at the previous x and the previous y. In this case, there is no previous y in that, so the previous y will not affect this part of the answer. Okay, so I start with my previous y, which is 1. My delta is 0.25, and I'm going to evaluate this at cosine of 2 pi times my previous x, and my previous x was 0. Okay, so I have the cosine of 0, which is 1, so this gives me 1.25. Okay, so now I take my previous y, how about that? I take my previous y, 1.25, plus 0.25 times the cosine of 2 pi times my previous x is 1/4 of 0.25. Okay, so 2 pi over 4 is the same as pi over 2, and the cosine of pi over 2 is 0. So this whole thing goes to 0, and my answer remains 1.25. Okay, I take my previous y plus 0.25, that's my delta x, cosine of 2 pi times, I'm going to write this as 3 over 4, 3/4, the same as 0.75. But write it as a fraction makes it easier because then I can write this as 3 pi over 2, and cosine of 3 pi over 2 is -1. So this becomes 1.25 times -0.25, which is 1. So we went back to 1. Okay, so this is 0.25. And the 0.25, remember, is coming from my delta x. That's why I'm using 0.25 each time. And this is cosine of 2 pi times 1, which is cosine of 2 pi. Cosine of 2 pi is 1. So then this becomes 1 times 0.25, which is 1.25. And that is the approximation at 1. Okay? Let's do one more example. Okay. In this example, we're starting off with initial condition, x is 2 and y is 0. And we're trying to get to f of 3, and this time it tells us delta x is 0.5. So we don't have to figure it out. So then we do 2.5 and 3.0. So in 2 steps. Okay? So remember, we always have to start with our previous y plus our delta x times our derivative evaluated at our previous x and our previous y. So this is going to be times my previous x is 2, my previous y is 0, and so that's going to give me 0.5. Okay? Alrighty, and then the next one, so then I take my previous y, which was 0.5, and I'm going to again multiply by 0.5. Now remember, this 0.5 is because that's my delta x. And I'm going to evaluate this with my previous x, which would be 2.5 over 2, plus my previous y. My previous y this time was 0.5 over 5. And using my handy-dandy calculator, I cheated and did this earlier, I got 1.175. Feel free to check my math if you like. Okay? So we always like to end with a free response question. So what I would like for you to do is I would like for you to pause this video and try the free response on your own, and then come back and watch the answer to the free response. Okay? So pause the video. Okay. Welcome back. Hopefully you paused the video. In this first problem, we notice that we need to do, it's asking us to find the limit as x approaches 0, so we're going to try a direct substitution. Now, I don't really need to know what f of x is. Let me just give you a hint. Generally, if they don't ask you to find the particular solution, you don't need to find the particular solution to find that answer. Now, in C, we will have to find the particular solution. But I noticed on your last test, a lot of you found the particular solution in A, which was fine because you ended up having to do it anyway. But that is unnecessary for this. It gives you enough information to do this problem. We're taking the limit as x approaches 0. So we just need to know what f of 0 is, doing a direct substitution. So if I do a direct substitution, I get the limit as x approaches 0 of f of x. So f of 0 is -1. I get -1 plus 1 over the sine of 0. And I get 0 over 0. What do we know about 0 over 0? What type of form is it? Indeterminate. And if it's indeterminate, what do we have to use? You are correct. We're going to have to use L'Hopital. Now, on last year's test, students were penalized if they didn't show that they had to use L'Hopital. So it's important that you first show that it's indeterminate. That's important because you'll lose points if you don't do that. And then secondly, you have to show that you use L'Hopital. So you have to do something like, I think they wanted you to write something like using L'Hopital. Okay, so using L'Hopital, we get f prime of x over cosine of x. And this is the limit as x approaches 0. And f prime of x, we have to then use this differential equation. So f prime of x, over cosine of x. Well, we know cosine of 0 is 1. Let's just go ahead and do that. So we have to evaluate this at 0. Well, we know when x is 0, y is negative 1. So this becomes negative 1 squared, 2 times 0 plus 2, which gives us 2 over 1. So our answer is 2. Okay? Now, using Euler's method, we're going to do the second part. Now, this was a calculator inact question, but it got a little hairy without using the calculator. So remember, you don't have to get a final answer. You have to set it up with the fraction. Okay. So using Euler's method with x equals 0 and 2 step sides to approximate f of 1/2. So that means that if we're trying to get to 1/2 using 2 step sizes, we're going to have to go start at 0, and then what size are our step sides? 0.25. So I have to do 0.25, and then once again I get 0.5 or 1/2. My initial condition, when x is 0, y is negative 1. So remember, we take our previous y value times our step size, and we're evaluating the derivative using our previous x and our previous y, which gives us negative 1 squared times 2 times 0 plus 2, because our previous x is 0. And if my math is correct, that is negative 1/2. Okay? So remember, I take my previous y, negative 1/2, times my step size, which in this case is 0.25. Then I'm going to take my previous y, which is negative 1/2. I'm going to square that. And then 2 times my previous x, which was 0.25, plus 2. And now, the answer, I can't remember the answer, but it's okay to just kind of simplify this and write this as negative 1/2 plus 1/4 times 1/4. So 2 times a fourth is, 2 times 2 over 4 is 1/2 plus 2, I think that's 5/2. That's a perfectly pretty answer. You know, that's perfectly pretty. So you could leave it like that, or you could do this. What is that going to be? 5 over 32. Or you could do that. Oh, and that's a plus sign in between those. Okay? So, but then they gave a final answer. I think it may have been like 11 over 32 or something like that. But that answer is fine. You can use your calculator to get that. Now, I am not going to do the last part because you should be able to do it, but I am going to give you the answer for it. And the answer is y is equal to negative 1 over x squared plus 2x plus 1. And what we found was that c was equal to 1 when we found our c. Okay? So that is it for Euler's method, and there is some practice for you to do. That's the end of video 1.